Okay, so we previously spoke about transformations and actions. So when we think about Spark processes, Spark can be seen as forming an application in Spark can be seen as forming a directed acyclic graph. So what is a directed acyclical graph? It's a graph that's directed without directed cycles. So we'll see some examples. So let's consider again that we have our data of clients or customers, items, the hour of the day, and the price. And we want to define before the number of customers buying each premium item per hour of the day. So we already saw this task. We won't go through it again, but we can represent the task that we saw previously as a directed acyclical graph where we have transformations that take two or more RDDs, or one or more RDDs, sorry. Well, except for load, which takes a file, so we'll say 0 or more RDDs. But in general, the transformations will produce a new RDD that can be the input for further transformations and actions. So we saw this job before where we load the data, we filter by the premium items, we reduce the number of partitions, which is mainly to give the example. We apply a distinct to make sure we only count each item per customer once. We apply a map, and then we count the number of item hour pairs. So we get the number of items per hour sold. So we can represent the task that we saw as an RDD. So let's say we wanted to change this. So this is, sorry, as a directed acyclical graph. So we see that there's no cycles here, right? If we had a cycle, it would be problematic because we would somehow need an RDD to be able to compute some transformation, right? We would have this sort of cyclical definition of an RDD, which we wouldn't be able to resolve. So we have a directed acyclic graph underlying the process in Spark. So let's say to this task that we previously saw, what we would like to do is take some information about demographics from, for example, loyalty cards that customers use. And we'd like to do some analysis of demographics, for example, females older than 30 buying each premium item per hour of the day to target a particular demographic of customer. So in this case, now we have two files that we'd like to read from. So we not only have our receipts.txt here, but we have some information about our customers, which we can also assume is on HDFS, for example. And if we look at this process, we'll need to load the data. We'll need to filter the data according to the demographic we wish to have, in this case, females older than 30. And then what we would like to do is join this information with the information about products coming from here, the premium products per customer. So in a join, as in the relational algebra, we take two tables, two relations. In this case, the join will take two RDDs, right? And then we can continue after that. We can, for example, apply a map and a count. So this allows us effectively to make sure that our analysis here is for general customers and our analysis here is for a particular demographic that we've selected. So we see that we can represent jobs or analyses or processes in Spark as a directed acyclical graph. Can anyone see a possible problem with this process? Okay. Excuse me. So let's say we call this action first. This is the first action we call, which is the analysis of products per item, products per hour for all customers. Okay. So let's say we apply this analysis here and then we do the count by key. So when we call this, we have to execute all of the transformations, the dependent transformations for that action. So we need to somehow now load the data, filter, coalesce, distinct, map, and then count by key to produce the output. When we define our other process here, and then we call count by key, what will happen? So we'll have to do the map, we'll have to do the join, we'll have to do the filter, and we'll have to do the load. But we also have to resolve this RDD, right? So this is also dependent, this branch here. So we'll also need to do the distinct, coalesce, filter, and load, again, possibly. right? So somehow if we're using the same RDD twice in two different transformations, it could cause problems like this, where effectively we have some duplicate processes because an RDD has two different branches of the directed acyclical graph are going to use that RDD. And those branches could call the dependent transformations more than once. Okay, so the problem here is we would have to apply these transformations twice. Does that make sense, or any questions? All good. Okay, so what's the solution? How do we resolve this problem? So the obvious thing here is these are representing virtual RDDs that don't really exist. They're just something we can reference, but they don't actually exist in memory. In main memory on this, they don't really exist yet. Okay. So what we can do is maybe think about materializing that virtual RDD and actually storing it somewhere, caching it, right? So there's the notion of a cache. So what we can do here is, okay, one option would be to write the RDD to the disk and then load it twice, right? But that's a bit inconvenient. We can call a cache operator in Spark, which will essentially create a physical RDD. So we see a solid line here, which means that this thing actually exists in memory, on disk, whatever, but it has been physically computed. And then we can pass that RDD to each of these. So essentially, okay, I should remove this link here. Sorry, actually, this link is no longer necessary. But anyways, so so now both of these processes are using this RDD, so we don't need to compute the transformations twice. So we materialize the reused RDD, the RDD that we're going to use several times, and we're going to use cache, or sometimes it's called persist, to do that. So the cache is still lazy. It's not that when we call cache on an RDD, it's going to run. But the first time we run, for example, count by key here, let's say this one, or it could be this one. First time we run it, what we're going to do is when we pass cache the first time, we're going to cache the RDD. Therefore, the second time we don't need to recompute this RDD. We can just reuse it. Okay, so it's still lazy. Okay, it's not when we call cache that will actually, execute all of these transformations needed to compute this RDD cached here, but rather will only call cache when it's needed for an action. Okay, so actions still coordinate when things are run. And you can decide if you want to use memory or disk or what you would like to use for this. Okay. So this is the idea of a cache, and it's quite common and quite useful to have caches. So in terms of the Spark lifecycle overall, what we have are input RDDs. So we can load them from disk, for example. We transform RDDs, we cache reused ones, RDDs that we're going to use several times. And then we perform an action, or we can perform multiple actions, and this will launch the execution or the computation of the RDDs, the dependent RDDs. So finally, we can then output the result of an action will be output to a file, a database, a local terminal, a local application, your local Python code, whatever it might be, but it's output to some external resource. Okay. So the key concept here is that we already saw our transformations, which are lazy. We saw actions, which launch executions, and we've now seen the idea of cache, where we avoid applying the same transformations repetitively, but rather we can use a cache to recall some data later in the process. So this is the kind of core of Spark, what we've seen. It's kind of like a mix between MapReduce and something like Pig. It provides more high-level operations, like we can directly call join now, for example, in Spark. But what we've seen is just the core of Spark. In fact, Spark is this very large library of different types of features, architectures, components for different types of applications. So what we've seen is sort of the core of Spark here, which is kind of equivalent to something like MapReduce Hadoop. We've not really spoken in detail about Yarn, but Yarn is a resource manager for Hadoop. It's essentially what decides on which machines will run which parts of the MapReduce task. So I'm not going to speak that much about administrating clusters so much in this course in terms of the administrative for system administration side of things. But Yarn is the resource allocator for Hadoop. And the equivalent here is Mesos for Spark, although Spark can use Yarn. And there's also been different types of distributed storage proposed for Spark, although Spark can use HDFS for at least for input for its RDDs. There are also a variety of storage, distributed storage formats. Aside from the kind of storage and resource management and the core programming framework, there are also sorts of libraries or extensions for particular types of tasks. So we saw like Hive, or maybe even something similar to Pig. You can write SQL type commands. Spark also has an SQL type plugin that will interpret your SQL-like query as Spark processes. There are also libraries for Hadoop for machine learning and a distributed setting, for example, Mahout. So Spark has Microsoft machine learning library, MLlib. We won't be speaking about this in the course. Storm. Storm is essentially a platform for streaming, for processing streaming data in Hadoop. So for example, if you wanted to process an incoming stream of tweets or sensor data from a factory, or maybe something like Waze, where you have positional information from people who are participating, and you need to process it and take actions based on that. These sorts of frameworks help, and we'll actually see a framework in either of these. Actually, we'll see a framework called Kafka later in the course for handling lots of streaming data. And there is a library for processing graphs, particularly for being able to apply graph algorithms. So if we think, for example, social networks like Facebook are graphs, where we have the nodes are users and we have connections that represent, for example, that a user follows another user. Graph processing or graph algorithms have become very important in different areas. There are extensions as well, particularly for processing graphs. And Spark has one called GraphX, and Hadoop has one called Giraffe. So the main difference is that while all of these here are sorts of like third-party extensions of, well, no, this is the core of Hadoop. While these are more like third-party extensions in different projects of Hadoop, okay, some of them are very well supported. These all are somehow part of the same Spark infrastructure. So the Spark framework is somehow much more feature-filled, in the sense that there are lots of libraries, different types of storage formats, and so forth. So we've just focused on the core, on how to code jobs on Spark. Any questions or? Okay. So Spark versus Hadoop. What's again the big deal about Spark versus Hadoop? The big deal is that Spark allows for using memory. So somehow that's the general kind of principle, I guess, on which it was built, to maximize the use of main memory available on the machines. So if you have a lot of main memory available on your machines, Hadoop doesn't really take care of that, because it always coordinates on the disk inputs and outputs, which is not necessarily the case for Spark, and that can make a huge difference to performance if you have a lot of memory. However, it's important to note that Spark can use the disk. So Spark can use the disk as a default, disk only, to avoid using main memory, to save it for some other tasks, or it can use the disk as a fallback as well. So there have been kind of studies as well looking at comparing, benchmarks for Spark, and a major aspect of the performance of something like Spark or Hadoop is how quickly it can sort data, because the sorting is the main operation for doing joins, for doing group by, and so forth. And the short message is that they have found Spark to be faster than Hadoop. But the big problem, okay, these results are maybe kind of old, but the big problem was that this benchmark was run by the people at Spark itself. So But in general, the idea that Spark can use main memory makes it more performant. And it also provides a more high-level way of expressing analysis tasks, coding these things up. So yeah, returning to the Google Trends, we see for that reason, perhaps Spark is becoming more and more popular than Hadoop, but both are still important in the practice of kind of big data analytics, let's say. That's it. That's the class. Any questions? Okay, so if there's no questions, we can start the lab. So in the lab, you're going to implement an analysis of some TV shows. You'll be given some data about TV shows from IMDb. You'll be given some information about the episodes of the TV shows and just the sort of high-level TV show themselves. And you will be asked to perform an analysis of the data associated with that. One thing to note is just that there's an important distinction in the data between a TV show and its episodes. So IMDb has pages for TV shows. For example, there's a page for Game of Thrones. Maybe not the best example. Nobody wants to think about Game of Thrones now, but there's a page dedicated to the entire series, which has a rating and the number of votes and so forth. But every episode also has a page, and they have ratings and numbers of votes. So what you will be doing is analyzing TV series, both the series itself, just that page, but also the episodes within that series. And you'll see, for example, if the average episode rating or the max or the min episode ratings correspond to the overall series rating, right? So is there, does somehow the overall series rating reflect the ratings of the episodes? So you'll be implementing that in Spark. So Spark you can implement in Scala, you can implement in Java, or you can implement in Python. In the lab, we're assuming, since we've already done tasks in Java, that the default is Java, but you can, if you want, try to program in Python. One caveat is that I don't have that much experience with Python. I'm from a different generation where we all did Java, but you can do it in Python if you want, using PySpark. And that's supported by the Spark framework itself. Possibly also another reason for Spark's success, in that it provides, there's lots of work in machine learning, for example, where there's lots of things done in Python. And that might make Spark a more convenient choice for machine learning, for example. But Spark itself is implemented in Java, Scala with the JVM. So there might be a performance cost, but at least in this case, Python is supported by the library itself. Okay, so if any questions or comments? Okay, so we can pass to the lab.